All right, folks, as we talk more about thermodynamics and get into some more of the finer details, what we want to do is we want to look at the effect that temperature has on the Gibbs free energy. We want to be able to determine the spontaneity of a reaction, and then we want to be able to pick the temperature at which a reaction may go from non-spontaneous to spontaneous or vice versa. So let's go ahead and we're just going to do a couple of thought experiments, I guess, or thought simulations. So recall that we know that delta G is equal to delta H minus T delta S. Okay, so delta H and delta S may be known for a process. So how can we change the spontaneity, if at all? So for instance, we're going to go through and look at all possible cases of endothermic and exothermic reactions, looking at delta H. And then we're also going to look at delta S leading to more disorder, so delta S being positive and delta S being negative where it's becoming more ordered. So here we can say that if delta S is positive, more disorder. If delta S is negative, more order. And we know that a negative delta H is an exothermic process, and a positive delta H is an endothermic process. So what we want to do is we want to, let's turn this into a game. What we want to do is we're going to use this equation right here. Delta G is equal to delta H minus T delta S. And we're going to figure out at what limit, so how can we change this temperature in such a way that delta G is negative. And that's if possible. We might run into a case where we can't make delta G negative regardless of the temperature. So for instance, if we rewrite our equation, we have delta H minus T delta S is equal to delta G. So to make a spontaneous process, delta G is negative. So if we were to look at this, if we have a negative delta H, so we plug in a negative value for delta H and a positive value for delta S, is there a temperature at which delta G is not negative? Well, if you have a negative minus a positive number times another positive number, because the temperature has to be positive because we're on the absolute scale. If we're looking at this, delta G is always going to be negative. So if you have a negative delta H and a positive delta S, what we'll see is you're going to have a spontaneous reaction at all temperatures. Well, what happens whenever now delta H is positive? So if you have a positive number plugged in right here and a positive number for delta S, how can we make delta G negative? Well, if we want delta G to be negative, we essentially have to cancel out this delta H. So what that means is we have to increase the entropic effects, or we have to increase the contribution of this entropy term. So if we need a larger contribution from that entropy term here, what we actually need to do is we need to increase the temperature. So what we could say is if you have a positive delta H and a positive delta S, this will be spontaneous in the limit of high temperatures. Okay, well, let's go ahead and look at another example here. What happens whenever we have delta H a negative value? Okay. Delta S is a negative value. It's starting to become more ordered. And we want to end up with delta G being a negative value as well. So if we look at this equation, now we want this term to dominate, okay? Because this is going to lead to a negative delta G value. So if we want to minimize the effect of this entropy term right here, what we need to do is we need to decrease the temperature, okay? So what we could say is that if you have a negative enthalpy and a negative entropy, this will be spontaneous in the limit of the low temperatures. In our last example, from more of a qualitative view, is what happens if you have a positive delta H, so it's endothermic, so it costs energy, and a negative delta S, meaning it's becoming more ordered. We'll come to find out if you have a positive delta H and a negative delta S, this will never be spontaneous. All right, so let's look at an example here really quick where we're actually trying to figure out the temperature at which a reaction becomes spontaneous. So if we were to consider iron metal can be produced by reducing iron 3 oxide, which is a fancy way of saying rust, with hydrogen. Okay, so whenever we are reading through this, we see this keyword spontaneity or spontaneous, so we know that delta G is equal to delta H minus T delta S. And then we're given a balanced chemical reaction here, and we're given delta H and delta S of this reaction. So is this reaction spontaneous under standard state conditions? And recall for thermodynamic systems that for standard state temperature is 25 degrees Celsius or 298 K. So is this reaction spontaneous? Well, we're going to plug into our equation. Delta G is equal to delta H minus T delta S. So we have delta G is equal to 98.8 kilojoules minus our temperature, which is 298 K. And then this is where you have to be careful because entropy is typically given in terms of joules per Kelvin, and enthalpy is typically given in terms of kilojoules or kilojoules per mole. So what I tend to do is I tend to convert my entropy into kilojoules per Kelvin. So recall that there are 1,000 joules in a kilojoule, so you need to divide your entropy by 1,000. So we'll end up with an entropy of 0.1415 kilojoules per Kelvin. And whenever we plug this in, we'll end up finding that delta G is 141 kilojoules. Well, if delta G is greater than 0, that means this is a non-spontaneous process. So what we need to figure out is what temperature will this reaction become spontaneous? Well, if we're going from delta G being a positive value to delta G being a negative value, what happens between a positive and a negative value? What we're doing is we're looking for a sign change. So we're really looking at delta G equaling 0. So we can take this equation, delta G is equal to delta H minus T delta S, and we can solve for the temperature. So in order to solve for the temperature, what we can do is we can end up rearranging this equation to get T is equal to delta H minus delta G divided by delta S. So we can plug in our enthalpy, which is 98.8 kilojoules, minus delta G, which is 0 kilojoules, over delta S, which is 0.1415 kilojoules per Kelvin. We can see that the kilojoules will end up canceling out, and we'll be left with Kelvin. And so we should end up getting 698 K. So it's 698 Kelvin, or 425 degrees Celsius. So what that means is, for this reaction to become spontaneous, we have to heat our reaction up over 425 degrees Celsius. So you can use this equation for Gibbs free energy to figure out at what temperature a reaction becomes spontaneous.